relative phases. Okay? We did this previously. We did this last time, I think. Voltage across resistors, I of T times R. And it's in phase with I of T. Okay? And we're assuming an alternating current, a sinusoidal current. If you have something else, you really got to get into Laplace transforms and stuff. And that's down the road a little ways. Okay? Elam's seen a little bit of it. So let him explain it to you. Okay? So, VC, voltage across capacitor, is Q of T over C. We did this last time, so I'm doing it kind of quickly. And this is (90 degrees behind the phase of I), and VL is Q double prime of T times L, and it's 90 degrees ahead of the phase of I. Now, our phasor diagram, we have V sub R let's just say it's V max cosine of omega T. So right now the angle here is omega T. Of course, as T goes on, this thing just rotates around here, and the actual current is the projection down here. Okay? Our actual voltage. So, when I say this is the actual VR, I really probably need to distinguish this from this, because this is a vector. It's got its initial point at the origin, rotating around here, right? So,
it's just the magnitude of VR, right?
well, this is, it's not just magnitude, because it's got a sign. It could be, you know, the actual voltage can be positive or negative, as you know, if the current is alternating, right? Voltage goes from positive to negative to positive to negative. So, without belaboring it, I was going to put a hat over this. And I'm going to say it's a vector, okay? So I'm waving my hands a little bit. We could make that rigorous. We put i's and j's on it. You know, cosine omega T times I plus sine omega T times J, right? And it's worth doing that, but not right now. We want to just get these phase relationships. I'm showing you where the phase relationships go. Did it last time, but you probably need to see it again. Okay, so we have the capacitor voltage, which is 90 degrees of phase behind this, so it's got to be here. Now, how long these vectors are depends on the reactance that we'll talk about, but not right this time. The reactance is simple enough, okay? Just omega C or 1 over, no, omega L or 1 over omega C. Okay, it's the degree to which the element, capacitor or inductor, suppresses the voltage. And again, inductors don't like fast changes. If you try to change voltage fast, you don't get much current. Capacitors don't like slow changes, in the sense that if you have slow changes, the voltage and the current just decrease for a long time. They continue decreasing for a long time, so you don't get much net voltage. Anyhow, then we got that, and then we got, then of course it's 90 degrees behind. And then we've got PL, and the current is 90 degrees behind the voltage of the inductor. There's our picture. We get a resultant of these vectors. These two add up to something about this long in this direction, so that the resultant will be this, and down here is our vector that represents so we'll call this the V total vector in the real world V total. Okay? And that's a phasor. It's kind of fundamentally cuts through a lot of nasty trigonometric manipulation. So it's a handy thing. So we want to understand that.